Hi, my name is Julia Billings, and I just finished my first year of biomedical engineering at the University of Guelph. This summer, I had the opportunity to work with Scott Brandon. Throughout the summer, I had the privilege to develop my understanding, skills, and knowledge on Artisynth and FeBIO. Artisynth is a 3D modeling platform that supports the combined simulation of multi-body and finite elements models, together with contact and constraints. I first started with a particle spring, which consisted of a simple particle connected together by axial springs. I altered the shape, color, position, velocity, and force of the probes and compared the results. Throughout the summer, I had the opportunity to use my knowledge from first-year coding, C programming, and apply it to Java. After working in Artisynth, I started modeling elements in FeBIO. FeBIO is a nonlinear finite element solver that is designed for biomechanics and biophysics applications. Within FeBIO, I've created and imported meshes, set boundary conditions, material properties, and different contact surfaces and forces. After creating a model, FeBIO allows you to run the model and calculate several different reaction forces. I first started with a leg model. The rectangle represents a leg muscle and the ball gets dropped, making a deformation into the muscle. From the results given in FeBIO, I was then allowed to calculate and graph von Mises stress from the simulation. Throughout my summer research with Scott, I also went through several different tutorials and situations to gain knowledge to navigate myself throughout FeBIO. I started with a billet problem by creating a finite element for a compression test where a rigid wall compresses a deformable mesh. Only one quadrant was needed for the model, as the mesh is so finite. Next, I worked my way through a simple tensile test. A rectangular box was created with a fixed prescribed end on the left side. A boundary condition was applied to pull one end of the box by applying a displacement. Next, I worked on a twisted bar problem, which consisted of a rigid body, which was connected to a deformable mesh. An applied prescribed rotation was added, which allowed the deformable mesh to rotate. Also worked on a biphasic unconfined compression. The geometry consisted of a cylinder to which a prescribed displacement is applied in the axial direction. The image shows the fluid pressure for 4 different time steps. Last tutorial I learned was a multi-step analysis where I created a beam bending problem where the beam is loaded statically. The load is then released and the dynamic response of the beam could be explored. After gaining experience in FeBIO, I could now start to model the data Scott provided me. Ultrasounds were sent to me from Scott, like the one shown. As demonstrated in configuration R, the subject is in a relaxed state and the compressions are applied on the anterior mid-thigh. I could now make a 3D finite model for the subject based on the ultrasound. As you can see, the ball acts as the probe. Rectangle is the thigh tissue. When run in FeBIO, we can now see the force versus displacement, displacement versus time, and force versus time graphs of the deformation. To make sure the model in FeBIO was correct, Hertz Contact equation was used to validate the values being gave in FeBIO. I'm so grateful to have been given the opportunity to be a research assistant this summer along Scott Brandon. I would also like to thank Scott for all his guidance and assistance along the way.